This is May-June 2025, paper 1-2. Question 1 says, what is the physical quantities have? And this is going to be a factual based answer, very quickly solved. A magnitude and a unit. Question number 2 proved to be a bit tricky this time. So this is what is 0.25 kilonewtons per millimeter square expressed in newtons per meter square. So we know that we can convert kilonewtons to newtons first, which will be 0.25 into 10 raised to the power 3. Now, to convert millimeter square to meter square, for that we can develop this ratio that 1 meter is equal to 1,000 millimeters. And since we're squaring this, let's take the square for everything over here, and then we can develop a ratio that this was divided by 1 millimeter square. So what if 1,000 squared millimeter divided by 1 meter square? Because we can manipulate this ratio to look like anything else. I can divide 1,000 by 1 or 1 by 1,000, depending upon what I'm looking for. So eventually we notice that millimeter square gets cancelled with millimeter square, and because there's a square over here, so we get all of these numbers multiplied together to get your final answer of option, it's going to be option D. Question number 3, a student calculates the density of a solid steel cube. In an experiment, the measured mass is this. And the measured length of each side is 50 millimeters. Now notice that this is millimeters, but the answers are given in centimeter cube. So we have to be careful about that. And what is the density of the steel with the absolute percentage uncertainty included in it? So let's first calculate the density. So the density should have been equal to mass, which is 975. Do I need to convert this grams? No, I don't need to do that because the answers are also in grams. But I do need to convert this 50 millimeters to 5 because 1 centimeter has 10 millimeters. So dividing this with 10 gives you a value in centimeters. So this should be 5 cube equals to, this should give you an answer of 7.8 grams per centimeter cube. Now comes the part with percentage uncertainty. So for the percentage uncertainty in density, we could have solved this like this. So this will be absolute uncertainties divided by relative values. So this will be 10 divided by 975 plus 1 millimeters. Now, here's an interesting bit. Do I need to convert this into centimeters for the percentage uncertainty? It doesn't matter. Why? Because if I was calculating this in millimeters, this would have been 1 divided by 50. If I was doing this in centimeters, this would have been 1 divided by 10 divided by 50 divided by 10. So it wouldn't matter because the factorization, or you can say the normalization dividing by 10 will leave you the same answer. So it doesn't matter. This and this should have been multiplied by 3. Why? Because the formula has cube in it. And for sake of percentage uncertainty, we know that for the percentage uncertainty or absolute uncertainty, we have to multiply or follow the power rule, which is going to look like this. And then the whole bracket gets multiplied by 100, giving you an answer of 7.025%, which will be 7% approximately, which is option B. Question 4. It suggests that time period of t. Now, t should have a unit of seconds. 2 pi is a constant, will not have a unit, but length is in meters. And then we have g as ms minus 2. So whatever we have inside the bracket eventually looks like something with s squared with raised to power n. If we want to make sure that this does end up looking like, let's say, seconds, then I need to finish out this square somehow. The only way I can do this is by taking an under or square root. So n should have been equal to 1 over 2, and that is the answer for option C. This time the question is very quick and fast. Question 5. A radio wave, now since we're dealing with radio waves, is the time between emitting and receiving the pulse is 3960. So we deal with this as an echo problem, right? So between the Earth and the planet Jupiter. So this is probably Jupiter. This is Jupiter and this is the Earth. So the signal was sent out and then the signal got reflected back. Now this whole time is measured as 3960. Now we need to know the distance between the planet and between Earth and the Jupiter. So this time needs to get halved, or whatever distance you've considered, that needs to be doubled. So there are 2 ways to look at this. This should have been speed equals to 2d divided by t, or speed is equal to d divided by t divided by 2, which if you notice is the same thing. If you manipulate this mathematically, it's the same thing. Now, the confusion is that the speed of the wave is not given, but we know that all the electromagnetic spectrum waves actually travel at the speed of light in vacuum. So this should be 2d divided by 3960. Now, the d in this equation comes out as 5.94 into 10 raised to the power 11. Now, be careful. Since you are taking the speed of light in meters per second, this is going to be meters. And now see how the examiner has been clever about this. He's given you the same powers here. So you mistake this option for that. But we know that this is in meters. And if you want to convert this into kilometers, this will be 10 raised to the power 8 by taking 3 out of it. This should have been option A in this case. Let's move on to question number 6. Question number 6 is given to you as a graph. And whenever you have a graph of kinematics, we always use the graph and the graphical techniques to answer the question. So you say, which statement is correct? The car accelerates for 2 seconds. Yes, for the 2 seconds it does that, but then it stops for 2 seconds. This is false. You see, even in this section from 2 to 4, no matter at what time you check, the speed is 12 meters per second. The car is still moving. It's moving at a constant speed, at highway speeds. You can say that it's moving in a straight line probably, and is not accelerating or decelerating. So the second statement was wrong. So that's why option A is rejected. B, the car accelerates at 12 meters per second square for 2 seconds. So no, it doesn't do that. You see, for the acceleration, that is the change in velocity divided by change in time. The velocity changed from 0 to 12 in a time of 0 to 2 seconds. So this should be 6.0. This should have been 6. The calculation is incorrect. The car travels a distance of 36 meters in the first 4 seconds. For the first 4 seconds, yes, let's calculate that. For the first 4 seconds, you could have divided this into parts very, very easily. And this part would be 1 over 2 into 12. And this part would be 12 multiplied by 2. So this comes out as 24 meters. This comes out as 12 meters. So 12 plus 24 becomes 36. So this seems to be the right answer. But let's move on to D. The car travels at 48 meters in the last 4 seconds. The last 4 seconds, if you calculate this, this is going to come out as 24 meters only, which is a false statement. This is wrong. So the correct answer of this option is going to be option C. Question number 7. He says a solid block of mass 1 kg falls vertically downwards in vacuum. There is no drag. And when it reaches a speed of 60 meters per second, an additional force of 50 newtons starts acting to the upward direction of the object. What is the speed of the object after 2 seconds additional force is acting on it? So first, let's analyze or find the acceleration. So the object is 1 kg moving downwards with a force of mg, which is 1 multiplied by 9.81, and then eventually experiences a drag of 50 newtons. So we need to find the deceleration, what the deceleration might be. So this should be F equals to ma. So 9.81, because it's multiplied by 1, minus 50, the stopping force, equals to 1 kg into A. The acceleration comes out as 40.8 meters per second square. This is the acceleration after it reaches 60 meters per second. And then we can use equation of motion, which is V equals U plus AT, because time is involved. So the final velocity because of this should be, if it happened when it was at 60 initial velocity, plus minus because of deceleration, definitely. This will be 40.2, but this acted for 2 seconds as T. So this also comes out as negative 20.4 meters per second. It feels like that if this much acceleration or deceleration happened for 2 seconds, it would definitely cause the object to eventually start going up again. Because if we're assuming downward direction as positive, right, then it would eventually start going up again, right? So this should be 20, but we're not required to go into such detail because we just want to find out the answer, so that should be 20. Projectile motion. Why does the path have this shape? So the reason it has this shape is because the air resistance and the horizontal component is generally unaffected, but the vertical component is affected by the gravity. And as a result of both of these things, it behaves this way. So let's see. The constant horizontal, no, it doesn't have the acceleration. It has a constant velocity in this direction. There's a constant horizontal velocity, yes it does, and constant vertical acceleration, yes it does. The stone has a constant upward acceleration, no. The constant, no, that's also false. You see, the gravity is only acting in the vertical direction, which is downwards, like this. And the stone has a constant upward velocity. No, it doesn't have a constant upward velocity. Why? Because in the initial stages, the velocity is very high, but as it gains height, it loses that vertical component. That vertical component starts moving downwards or creating itself downwards. So the only correct option is option B. Question 9. It says rocket engine ejects 90 kg of exhaust gas per second. This is important, at a velocity of 190 relative to the rocket. What is the force acting on the rocket due to the ejected gas? So this is simple F equals to change in momentum divided by time, which will be m multiplied by v divided by t. Now you need to fit things into this equation. So if you notice that this is 90 kg per second, so m by t can be extracted as what this value is given to you. So this should be 90 multiplied by the v given to the question is 190. So this is 190, 19 to 190. This gives us 17,100 newtons. And this becomes option B. Question 10, it says, which statement does not describe an elastic collision between two objects? This is the true energy is conserved. This is also elastic. The total energy is reduced. This is not elastic. This should be the answer because that's what he's asking us. The total is linear momentum is conserved. This is also elastic. So C should be the answer for this question. Always in these questions, please pay attention to the word not elastic or is elastic. That's how he causes confusion to the children. The cyclist is riding at constant speed. This is an important keynote. On a level road, according to Newton's third law of motion, what is equal and opposite to the backward push of the wheel on the road? So if this is the road, this is the wheel. If the object has to go, the cyclist has to go in this direction, they need to pedal in such a way so that the tire exerts a force backwards. So this is by the tires. This is by the tire, but it is on the road. Now, what the road does in response to this is it applies a force in the opposite direction. So this direction, this green arrow is by the road, but on the tires. So in this case, he says that if that's the action force, then the forward push off the road on the back wheel will be the reaction. Yeah. Let's move on to question number 12. He says, what graph is shown for the acceleration A of the stone? So for the long distance in air, this is a key for us to think that it will eventually hit terminal velocity. If it is terminal velocity, the acceleration has to become zero eventually, or has to reduce to a very tiny value. Now in this case, he suggests that the acceleration is increasing, which is the false case, because we understand that according to F equals to ma, weight minus drag equals to ma. Drag is dependent on the speed of the object. As the speed increases because it's falling down, the drag increases, reducing the resultant overall. If d increases, the whole resultant decreases, and leaving us with smaller acceleration. So it should reduce with time. So option A is false. Option C is also wrong because it suggests constant acceleration. No, this would have been the case if this was vacuum, but it's not. And the case B is plausible, but the problem is that this is a non-linear equation, the non-linear behavior, because of the involvement of speed and drag in this case, and this leads to a non-linear equation which has some power factor in it. So this will be most likely be option D. The best answer is this option D. And this is a repeated question in terms of its presence in the question or questions in past papers. It says an empty cart moving along with a horizontal constant velocity. Resistive forces are negligible. The heavy rock dropped vertically on the cart. And what is happening in the vehicle? The cart continues to move horizontally with a rock inside it. How does the momentum and the kinetic energy changes? You see, the momentum generally never changes, right? So when he says has a smaller momentum, this statement is false. It has to have the same momentum. But when he says that smaller kinetic energy and same kinetic energy, this is where we have a debate. And now let's see, mathematically speaking, that if the momentum is same before and after, should the velocity have been the same? Because the kinetic energy is half mv squared. So let's find out the velocity after the rock was placed in it. So this was m1 of the trolley, velocity plus 0 of the stone, because it was not a part of the trolley initially, equals m1 of the trolley itself plus m2 of the stone into v dash, new velocity, because a new mass has been introduced into the system. And this is generally, if you find in my videos, this is the case of embedding, when a bullet is fired, let's say, in a wooden block, or when two objects collide and they start moving in the same direction collectively. Now, V dash is what I'm looking for. So the V dash is going to be equal to M1V divided by M1 plus M2. And certainly, even if you isolate V in this becomes M1 divided by M1 plus M2 multiplied by V. Because of this factor, the whole answer is going to get smaller. V, even if it wanted to continue with its old velocity, it couldn't have, because the mass is now increased, so the V dash new velocity is smaller. So if I were to apply the formula in this with a smaller V dash, the kinetic energy after the collision, even with a greater mass with M1 plus M2, overall the energy would have been smaller, because V squared has a more drastic effect, mathematically speaking, as compared to this one. So it should be smaller kinetic energy, is option C. If you go to, for example, in OCR, PSN Edexcel, or other A-level courses and syllabuses, you will see that they are using another formula for this justification. That is, kinetic energy is equal to momentum squared divided by 2m. And it suggests that, and of course, you can make this formula from, half mv squared compared with mv. You can eventually land to this equation. What should be squared, what shouldn't be squared, and so on and so forth. So he says that if the mass is increased while keeping the momentum constant, the kinetic energy falls. This is absolutely right, but I believe that this is the way to think about this, in terms of, if you do have a mathematical capacity to work it like this, and the proper logic should be this. Otherwise, this is a summarized version of the same logic. No matter what, here it's up to you. Here, the question number 14 suggests that a block is held stationary in water, and this seems to be like a case of upthrust, because it's water, and the wooden block has a small mass m, volume v, density of the water is rho, the acceleration of free fall is g. It says, what's the magnetic force acting on the block due to the tension in the spring? You see, let's find out all the forces where they are acting. So the mg should be downwards, the tension should be downwards, and then there should be an upthrust F up because of rho GV. So since the object is held stationary, that means all the forces are in equilibrium. All the upward forces are equal to all the downward forces. So upthrust should be equal to the tension plus the weight mg. Now, since he's asking me about the tension in the spring, I have to take mg on the other side. So this becomes T equals to the upthrust minus mg. And we understand that from Archimedes' principle, the upthrust has a formula, rho g capital V. So this will be rho gv minus mg is the tension. So this answer should be option D. All right, question 15. He says a square sharp sign has uniform density. Okay, fine. Its mass is 2.4. Length is given. There's friction in the hinge, which prevents it from coming back down again, and it's stuck at 15 degrees angle. By the way, this is a repeated question in the past papers. And he says, what is the moment about the hinge of the weight of the sign, which is still there, but the friction is trying to stop it? So the weight appears to be at the center of the sign, right? And we understand that the moment, or the only force responsible for bringing it to the mean position, is always mg sine theta. And this is actually like the slanting slope question that we so often discuss, that we have this mg, this is theta, this is cos theta, this is sine theta. And this is the component that is responsible for bringing it back to the mean position, or taking it away from the starting point. So mg sine theta is the moment force. 0.86 has to be divided by 2, because the center of mass, or center of gravity, is at the center. And let's do that. So the total moment at the hinge, experienced by the hinge, should be, because of the weight, which is, or the component of weight, which is mg sine theta, multiplied by 0.86 divided by 2. So ultimately, we have the weight given to us in the question, that is 2.4. We have the length, we have the angle, everything is with us. So this will be 2.4 into 9.81 into sine of 15 degrees multiplied by 0.86, whole divided by 2, or just 0.86 divided by 2, whatever suits you. This is going to come out as 2.6 Newton meters, which is going to be option A. Question 16, again, is a repeated question. If you're done for the, let's say, last 10 years of past papers, you would have encountered this question. And by memory, you would have landed on option A, but let's analyze why option A is the right answer. You see, to scale, all the forces are drawn, or all the arrows are represented to you. Now, let's see how that works, okay? So if all of this was submerged under liquid, let's say it's a very large container, right? And whatever density, whatever G is already there. So the pressure due to liquid is, we understand that's rho GH. Is the H that creates the problem, the depth. So from, let's say this is the top of the liquid, and the depth is going to be from top to this point, then top to this point, then top to this point, and so on, top to this point. Notice that these arrows should be exactly the same length. Why? Because rho GH to this point should be equal to the rho GH to this point. Even the tiny small, there should be a tiny difference, but on a larger scale, it shouldn't matter. But as you go down, the pressure should increase, which is only shown in option A. And the last arrow on the side and the last arrow on the base should be exactly the same length. The same logic applies on the top part. If you notice this in B, almost everything is missing, right? And similar thing with C. Now C has a problem. The problem is that this arrow and this arrow should have been the same because we're dealing with pressure. And the depth at this point and the depth from the top of the liquid to this point is almost equal. They should produce the same answer. So you should have had the same arrow. So C is rejected, B is rejected because of the missing side pressure, and D is also rejected. The top and the bottom are almost correct because the top pressure should be less and the bottom should be higher. But it's not progressively increasing. It should be greater and greater and greater because a higher depth leads to a bigger mathematical answer, which is not being shown in D. It's option A. Question 17 is again fact-based question, very quickly solved. The diagram shows a couple of forces, perpendicular force between the distance, and we understand this is going to be something related to torque. Torque of a couple is any one force multiplied by the distance between the forces, but the condition is they should be at 90 degrees to each the distance, and the force should be at 90 degrees. So half into perpendicular between the force and line, no, this is not the correct answer, is F into this D, total D. Between my one forces, yes, this seems to be the right answer. Between my sum of the, no, it's never the sum of the force, this is wrong. And 2 into, no, it's not 2 into, it's just simple one distance, one force. Should be B. Question 18. 18 says a ball of mass 1.2 kg horizontally at a speed of 3 meters per second. There's a cushion, comes to rest, horizontal distance this much. What is the work done by, now this is a repeated question in terms of the idea that the train, there is a train speeding towards the station and it needs to stop within a certain distance. How would you stop this? What's the braking distance? What's the braking force? It's the same idea I'm going to be using here. So the ball already has some kinetic energy which needs to be removed from the system. So the energy in the system is dependent on the kinetic energy, which is half into 1.2 into 3 squared. So it has 5.4 joules of energy in it. We need to remove this energy completely to make sure that it comes to rest. It needs to stop. So energy, and to stop this, I need to do work against it. So work done should be with a force up to a certain distance. The distance is given to you that a certain force has been applied to a certain distance or up to a certain distance by the cushion on the ball to stop it. So for us to remove 5.4 joules of energy by applying a certain force in the opposite direction to the movement of the ball, for a distance of 0.02 meters, the force comes out as 270 newtons. Right? The question generally ends at option C, but this is an extension to this part, that how you're supposed to look at this. Okay? All right. And the same logic applies to the braking force of a train, of a car, and that's how they design what the braking force of friction, at least between the tires and the road, should be. Question 19. A box has a mass of 4.9 kilograms pushed along. Now, this is the hint that you will always ignore as an A-level student, but I'm going to show this to you that this is very important. Constant velocity. This is always going to be the savior of the question. He says that from point B and onwards of an inclined plane, everything is self-explanatory. He says that the box is being pushed by 64 newtons parallel to the slope, which is shown to the diagram. The slope is inclined at an angle of 20 degrees and through a vertical distance of 5.8 meters. Everything is almost given to you. He says, what's the work done against a frictional force? Now, first job is to find the frictional force. Now, since he says a constant velocity, that means that the forward force, which is 64, should be equal to the friction. But is there only friction between the block and on the surface? Yes, but is there anything else that the force is working against? And that is the weight. So the opposite direction, it should be the mg sine theta that is working with friction to trying to stop this from going up again. So the actual driving force is equal right now to mg sine theta plus friction. They're both working against it. And why have I made them equal? Because it's constant velocity. It can only happen if the object, by whatever force it's being pulled, the pulling force and the stopping forces, or the sum of all the stopping forces, should be exactly equal. And that gives us the confidence that we can do this, right? So FD, the driving force 64, is given to me. This is 64 equals mg sine theta is also given to us. That is 4.9 kg of mass, because we will need to find the friction first. So this will be 4.9 into 9.81 into sine of this angle 20 minus F. Now the friction comes out as, in this case, is going to be about 47.5 newtons. Now we use this with the distance combined with whatever distance it has traveled at this angle up to this height, and then we can find the work done. So let's find the height that it has traveled, or the distance it has traveled. By using the trigonometric ratios, we can find out that the slanting slope distance it has covered between, or for that time duration, is going to look something like this. So this is 5.8, this angle is 20. I want to find this distance. The distance should be equal to 5.8 divided by sine of 20. So my work done should be equal to force into distance. My force is 47.5. 47.5 multiplied by 5.8 divided by sine of 20. This work done comes out as 806.5 joules. So this is going to be 810 up to two significant figures. Question number 20, again, straightforward question, very quickly solved. This should be C, because the energy and energy should be the same. And it's never the wasted energy, it's the useful energy. If you add the useful and wasted together, that equals the total energy, so it defeats the purpose of efficiency. Total energy input, no, it should be in reverse. That's the wrong thing to do, and this is why it's C. So we're skipping this over, saving time. Question number 21. Now copper, and then we have steel. Copper generally is softer. This is a general understanding. This is softer, more malleable. This is stiffer, more solid. They have equal lengths and cross-sectional areas. The student has an identical load, which means that the force is going to be the same on the two wires. The extension of the two wires are different. We understand that because copper is softer, is different. He says identify whatever Young's modulus was going to be is equal for both of them. You see, stress is force over area. If they both have same cross-sectional areas and you're applying the same force on them, the stress is going to be the same. But what about the strain? You see, strain is change in length divided by length. They do have the same original length, but they are not stretching by the same material, which means Young's modulus and the strain are going to be different. Why? Because Young's modulus is also stress divided by strain. They both have the same stress in terms of mathematical value, but they have different strain because they're stretched by different values. And copper stretches more than steel for the same physical dimensions, which is why only stress is the same for both of these wires. Question 22. He says two springs X and Y are stretched. Okay, fine. All the statements are given. It's up to you to check all of them, right? And the only one that's acceptable in this case is option B. Let's check this equation. He says given the same extension. And the way we're going to do this is to see that if this is up to 5, if this was up to 5, this will likely be at 10 newtons. So we apply the formula half Fx for both of them. So this is half into force, which is 10, into extension, which is 5. Again, this is centimeters. So 10 is to the minus 2, although it wouldn't matter because we're just comparing energies, but still. And this should be half into 80 into 5 into 10 raised to the power minus 2. Whatever energies you find, there will be a difference of 8 times, which is very evident. You see, half is same in both of them. 5 centimeters same in both of them. The only difference is 10 and 80. You don't need to calculate this. You just need to write it down, which is going to be option B. Question 23. It says, what phrase describes the strain and the elastic limit on the stress strain graph? And stress strain graph is generally for the Young's modulus graph. The maximum is always the minimum stress above which the deformation is plastic, but it's not breaking down. It breaks down when it is beyond the stress. When the force over area stress gets too much, that's when it breaks. Right now, it's just going to deform or get deformed. So the minimum strain above which the deformation is plastic is going to be option D. Let's move on to the next question. That is question number 24. A teacher removes the turntables of a microwave, and this is a very common question now. This is also done in demonstrations, classrooms. So it says that the turntable was removed in a microwave, and they placed a chocolate in it and turned it for a very short amount of time, and they found out that the chocolate bar, for example, if this is what the chocolate bar looks like, was actually melted from 2 spots, nothing else. If you had places on a turntable and let it happen, the whole chocolate would have melted, but that's not what we're doing right now. So he measured that the distance between the chocolate bars, or the distance between the 2 hot spots, is 6 centimeters. Now he's wanting you to find out that what is the frequency. You see, this happens when the stationary wave is actually an antinode system, because only at the antinode the displacement is maximum, the maximum energy can get transferred. So it should look like this. So basically, if you notice that the distance between one antinode and the second antinode is generally half a wavelength, which is why the 6 centimeter mark is actually half the wavelength, right? So this should be V equals F lambda. So this should be 3 into 10 raised to power 8. Frequency is what we need to find out because it's all hertz. And lambda, if you want to find the actual lambda, then 6 should be multiplied by 2 to get the single wavelength. So this is 6 multiplied by 2 divided by, in centimeters, divided by 100. And this frequency comes out as 2.5 into 10 raised to power 9 hertz, which is 2.5, yes, gigahertz. And now notice that the prefixes that you are so much avoiding, they become a part of the answers. Question number 25, again, this is a repeated question. He says that the sound wave travels from left to right. For example, if this is the speaker, the sound is traveling from left to right. This is what he means by that. So the particles are vibrating forward and backward in this fashion, in this manner. All right, so the displacement to the right, that is the positive. So displacement to the right means that if I look at the single particle, the life of a single particle, from the source, this is the speaker, where the speaker is going to be placed. That is the distance of the cone from the cone, right? So this is the particle that's not vibrating at all, and the particle at A is vibrating to the right side. All the particles in the middle are also vibrating to the right side, but A is on the maximum positive right side. Now, exactly at B, you will find that there are more particles between A and B that are still trying to go to the right side because the displacement is still positive. The B particle is not moving at all. But the particles after B are going left. And the C particle is going left the most, or is trying to go to the left. These particles are also going left, left, left. And exactly at D, the particles stopped moving again. Now the question he's asking is center of compression. If you notice that the compression center is actually at point B, because only at these points, all the particles are coming or trying to come close to, these particles are moving to the right, these particles are moving to the left, and they're only coming towards B. B is not moving at all. So B should be the center of compression. Question number 26, he says a buzzer is emitting sound frequency 846, string attached. The buzzer is moving at 25 meters per second, which means that it is coming towards you at that moment with a speed of 25 meters per second. He says sound is 340. This is a question from Doppler effect. What is the maximum frequency heard by the observer? It's only heard when you're moving towards it. When the buzzer is moving towards you, it's moving away. The frequency actually generally falls down. In order for us to figure this out, this should be F equals to 340 divided by 340 minus 25 into the frequency that is being produced, or standard frequency. So f dash actually by the observer is going to be 913.1414 hertz, which is option D. Question 27, again, a repeated question from waves and polarization and Malice's law. He says that the intensity on the outside is I by 3. The introduce is I naught. He says, what is the angle? So it goes like this, that this I intensity after the filter, I naught, introduced intensity, is cos square of theta, the angle that it was displaced from. So this I is given to us as I divided by 3 compared to the original. So if you check this out, this is going to be cancelled out, and we are left with 0.333 equals cosine square of theta. You take the square root on the other side, and this becomes cosine theta, square theta equals to 0.33. You finally calculate the answer, and theta comes out as 54.7. Of course, don't forget the square. And this will be 55 up to two significant figures. Question number 28. He says the statement compares the behavior of transverse and longitudinal. This is again a repeated question. I'm sorry, but if you've done questions of the last 10 years, you will find that these questions are all repeated. That's how you save time in A1. He says only longitudinal waves can be diffracted, which is a false statement. They never diffract because they're moving forward and backward through the gaps. Longitudinal waves can travel in free space. No. Longitudinal waves are sound, and then there is one more wave that belongs to the earthquake cycle. Only transverse wave can be coherent. Not really, even the longitudinal ones, because sound waves can also do that. For the diffraction pattern to emerge and for the interference to get established. Only transverse wave can be polarized. Yeah, that's true. That's a fact, and this is option D. Now, if you've done the past papers more frequently, you will realize that question number 28, you will quickly jump to option D. You will not be thinking or wasting time with other options. Question 29 is a bit interesting. It requires a bit of mathematical manipulation, but don't worry about this one. This is students use the diffraction grating to determine the wavelength of the visible light from a source. The diffraction grating has 300 lines per millimeter. And I explained in my videos that how to tackle this problem, interestingly, and being more clever. So the student measures the angle theta of each order, intensity maxima, the graph, n is sine, everything is explained to you. It says which expression gives the wavelength in terms of the gradient. So the formula that we're going to start with is n lambda equals to d sine theta. Now let's rearrange this equation based on what's given in the question. So if I were to find out the gradient of this equation, this should be y divided by x, and that is n divided by sine of theta. Can I do something with this equation in which I can manipulate this into thinking like that? And yes, I can do that. So if I bring sine theta to the other side, this becomes lambda multiplied by n divided by sine theta, which he's referring to as the gradient g. So I'm going to change this I'm going to change this representation. For example, this is equal to still d. We'll change this to be represented as capital G multiplied by lambda equals to d. Now let's rewrite this equation over here. So this is lambda equals to d divided by g. Now what is d? D was this value given to you in the question, which is 300 lines per millimeter. And now the method that I've explained to you is this, that whatever written after, just put this in the numerator, which is 10 to the power minus 3. And whatever is written before goes on the denominator. Now when you solve this first and then divide it by g, then you will get to this value, that this is 3.3 into 10 to the power minus 6 divided by g, which is equal to lambda. Should be option C. Let's move on to the next question. This is question number 30. Two waves meet. This is most likely going to be referred to as interference, or is going to go towards interference. What is not necessary? Not a necessary condition for waves to produce stationary wave. Okay, they should be at the same time. Yes, because we cannot add light with sound. We cannot do that. They must be the same period. Yes, they do. They must have the same wavelength. Yes, they do. They must travel in the same direction. No, they should be traveling in the opposite directions. Because if the producer is coming this way, the reflected wave generally comes from this way for the sound wave. But this is not necessarily true. So the best answer would be option D. 31. Now I'll show you a new technique to solve 31. You might have done this before, but let's do this again. And this is again a repeated question. A light of single wavelength is incident single wavelength, which means we can discard lambda if a new situation arises. Normally on a double slit experiment, interference fringes are observed on the screen. Okay, fine. The distance between the double slit is this. Fringe separation is this. The distance from the double slit to the screen increased by. This is where he's changed the question. It used to be is increased up to 0.9, which meant that this is the new value. But no, he's saying that this is increased by 0.9, which means that is more than 0.6, 0.6 plus 0.9. But let's see how to develop this equation. So the starting point is AX equals to lambda D. What are the variables that we don't need to think about? Now, since he's talking about a single wavelength for both cases, the lambda goes out of the question. It's a double slit experiment, and since he's not changing the gap between the slits, this is the gap A, he's not changing that, so we don't need to think about the A as well. So let's do the equation, which is X being proportional to D. Let's use this equation to set up a system that's easy to think about. This is where the technique comes in. This is what we're going to do to make it easy. So X new equals D new divided by X old or previous divided by D old. And now we're just replacing the value. So let's replace the value. So this will be, I'm going to continue this on this side because I'm running out of space. All right. So X new is what we want to find out. So Xn divided by the X old was 1 point something. Yes, 1.8. So this is 1.8 equals D new, because it's increased by 0.9. This is going to be a translation error. So this will be 0.6 plus 0.9 whole divided by the old D, which is 0.6 still. And when you solve this by bringing 1.2 to the other side, this X new comes out as 4.5 millimeters. So the new thing about this is this way of doing the question by eliminating the factors that are not part of the question at all. So let's not carry their weight throughout the question, and let's make it simple. Question 32 is that the wire is made of constant resistivity. There is a constant current in the wire, which potential difference. So the Ohm's law is V equals to IR, and we understand that the resistance equation is rho L over A. So as you move along the length, as you increase the length, the potential difference increases, or you can say that as the electrons move along the length, they lose energy. They require more work done on them to be able to do that. So when he says that it's directly proportional to the length of the wire, this is the most appropriate and best option because that's what we see. V is proportional to length. Question number 33. He says IV characters are given, which obeys Ohm's law. This one does not, and this is going to be the behavior of a diode. This is the threshold voltage when it switches on, when it's forward biased. And I'm not sure what component is this, but this is not obeying Ohm's law. It should be passing from the origin with a straight line. So option D only. Question number 34 is a numbers problem. We've already done this, but let's get through with this. So he says 200 ohms with 4 volts, 4 seconds. This is V equals to IR. 4 volts available. Current multiplied by 200 ohms resistance, which is this one. The current in the system is 0.02 amps, right? And since he's asking me about the number of electrons, I can use the equation Q equals to I multiplied by T. So Q is equal to I, which is 0.02 done for 4 seconds. But we understand that one electron has a charge of 1.6 into 10 raised to the power minus 19. So how many electrons do have a charge of 1 coulombs? So if you do this in reverse, you come back with a value that one packet of electron, or this one packet of coulomb of charges, actually possess 6.25 power 18, which is found by inversing this value. So simply do this. So 1 divided by 1.6 into 10 raised to the power minus 19, you get to the final answer, which is option C. But if you want to remember this the other way around, for example, that 1 coulomb of charge or one packet of electrons contains 6.25 into 10 raised to the power 18 electrons, that's up to you. But we get this number by doing the ratio method, by thinking about this in reverse, like this one. Question number 35 is a bit tricky. And for this, I'm going to zoom out the screen a bit, because it's going to require a bit of equations or manipulations, but we need to be able to observe the full question at all times. Okay, there's going to be a variable nightmare. Okay, so just hold on to the question and please bear with me. So read the question peacefully and make whatever equations you want to make. Pause the video and try this on your own, what equations you can come up with, because I'm going to dive straight into the solution of this because I don't have enough time. I have to finish this within the time frame. All right. So first things first, I'm going to start with the basic equation in terms of what we already have. So can I figure out the EMF of the cell? The EMF actually deals with the internal resistance and the external one. In the previous case, or the initial case, is 2R. So the total resistance of the circuit is 3R, and the current of the circuit is I1. So EMF is equal to I1 into 3R. So I'm left with I1 into R, 3 times I1R. Do I have a potential difference of the terminal potential difference, which is, let's say, refer to this as V1. So this should be on the outside. V1 or voltage 1 is on the outside. Like we're thinking what's available to the resistor. So it should be I1 multiplied by 2 times R, which is going to be 2I1R, right? So this is our starting point. Now we move on to the new situation for the comparison, right? In the new situation, since he has increased the resistance from 2R to 4R, we don't know what's going to happen to the current. So the equation would be that the EMF is equal to I multiplied by R. The EMF is already standard. We are not changing the battery. So this will be 3 times I1R equals I dash, because there's a new current, multiplied by 5R. Why? Because 4R plus 1R. And now we can see this very clearly, that this I dash, because R cancels with R, and since we're finding I dash, 5 goes over there. So this I dash new current will be 3 times I1 divided by 5, which comes out as 0.6 times I1. This is the first answer that we have for the current. It should be 0.6 times I1. We are very sure that option A and B are not possible. And by simple idea, simple basic logical analysis, if the current has changed, it's not possible that the terminal potential difference also remains the same as V1. It's not possible. So it should have been 1.2 or less or more, something like this. But let's see, let's calculate this. Even if you were doing this by intuition, it should have been D. But let's solve this. So under the new circumstances, the potential difference or the terminal potential difference should have been current multiplied by the resistance. The new current in the circuit is 0.6 times I1. So this is 0.6 times I1. The new resistance in this time around is 4R. Why? Because I'm thinking about the terminal potential difference. That is this one across the load only. What's coming out of the battery after settling the internal resistance? What are we getting on the outside? This comes out as 2.4 times I1R. And now if it's a comparison of voltages, right? So this is, if you compare this with the original voltage, V1, which was 2I1R, today's voltage, terminal potential, is 2.4 I1R. So for the sake of comparison, this will be 2.4 I1R divided by 2 I1R. I1R gets cancelled out completely, and we are left with 2.4 divided by 2, which is going to be 1.2, right? So this is going to be 1.2, option D. All right. Let's move on to question number 36. This is quite easy and straightforward. He says that the ammeter readings are identical, which means that whatever is happening, it should have produce a constant reading. So notice that if we go with A, there will be no current in the circuit at all because the circuit is not complete, right? And for the A1, there will be no reading because if we follow the option A, there is only one resistor here. There is no wire connecting here. And then we have a resistor connected at this point with no potential difference applied in the circuit. So there's no current in this option, but there's some current in this. He says that readings are identical. It's not possible for option A to survive like this, right? Okay, so option A is not possible. We've cancelled this out. Option B is going to create a problem. You see, if you imagine that the source is connected here, then all the current will be passing through branch 3 and 4. This is a short circuit condition. This amp will be higher and this current will be much smaller. So again, we're looking for a system that produces identical results. So this is not going to be the answer. Option C seems to be the appropriate answer because there is a resistor connected here and there's a resistor connected between these wires, right? Like this. And there's a connection here. So the connections are complete and the current coming through this will be shared between the two branches since they're identical. The resistors are assumed to be identical. So it should be option C. In option D, the current coming out and option D as well. So what could be the problem? So option C, in option C, if you look closely, you see the R1 is connected here and R2 is connected here. with the connection complete. You see this ammeter is showing you the full current coming from the battery. So half of it goes here and half of it goes here. This, for example, is 2 amperes. For example, if this is 2 amperes, this will be 1 ampere. Are these both identical? No. So it can't be C as well. It should be D. This is the only way this could produce an identical value under these circumstances. Right. Let's move on with option 37. So question again, from memory, based on what you've already done, this is going to be option A. I'm not going to waste my time here. But just for the sake of revision of notes, option D would have been the answer if he was asking about second law. So 37, two neutral atoms are isotopes of the same element. Again, fact-based question. Option B, straight off. Moving on to 39. Meson, it again is a memory-based question. So, but I'm going to show you a small tree. So we start with hadrons. On the other side, we have leptons. That's not important because these are electrons and neutrinos. For hadrons, we have barons and we have mesons. Mesons have 2 quarks. One is a quark and one is an antiquark. Barons have 3 quarks, mostly neutrons and protons. So he's asking you about what is a meson. So it has 1 quark and 1 antiquark, which is made of total 2 quarks. There's going to be option A, again from memory. Question 40 is a bit tricky, is a bit lengthy, but it's not that big of a deal. So he says carbon 12 is decaying to be this. Carbon 12, which has 6 protons, 5 neutrons, you should be able to figure this out. This is going to be 11, 6. Decaying with beta emission should be 0, -1. This is beta positive emission, so this should be +1. And this should lead to X 11, 5. Now, whoever this X component is, we are not sure, we are not required to memorize it, is asking about the up quarks and down quarks. So let's do that first. So it has 5 protons, which are made out of 2 up quarks and 1 down quark. And if I were to count the protons, that will be 11 -5, which is 6 neutrons, made of 1 up quark and 2 down quarks. So this should be of up only, all the up quarks, this should be 5 into 2 based on this, and 6 into 1, plus 6 multiplied by 1. All the down quarks should be 5 into 1 as 5 plus 6 into 2. So the up quark comes out as 16 and the down quark comes out as 17. This should be option B. That is all for today. I'll see you around.